So this section is vector valued functions. I think you will like this section. If I can ever get it to go where I want it to go so I can type. Okay, so we are going to define first, I'm going to do it in 2D and then I'm going to do it in 3D. Okay, so in 2D, we're going to define a vector. So let's let R of t be x of ti plus y of t j. Okay, so now this is almost like what we were doing before, except we're going to actually, I'm already messing up. I want this to be F and I want this to be G. Okay, otherwise known as R of t is equal to xi plus yj, okay? So R of t is a vector valued function which determines the position of a point. So R of t is a vector valued function that determines the position of a point. Okay, so now this should look familiar to you because before when we were talking about the vector that described the line, we had R of t, if you remember. So let's say for a line, we had R of t equal to x of ti plus y of tj, where R x of t was x naught plus at, and y of t was equal to y naught plus bt. And that was in 2 dimensions, we defined a line. And for this line, if you remember, the initial point P naught was x naught, y naught, and it had a direction vector v that was ai plus bj. Okay, so that's what we did for a line. Now we're going to have any old kind of curve. Okay, so it might not necessarily be a line. All right, so here now, x is f of t and y is g of t. So I can tell you exactly what those things are. All right, so for example, I can have r of t is equal to a cosine of ti plus a sine of tj. And as you can see, x of t is a cosine t, y of t is a sine t. And how nice is it that x squared of t plus y squared of t is equal to a squared. So this is a path that traces a point about a circle of radius A. And I need to tell you 0 for this one, less than or equal to t, less than or equal to 2 pi. So this one is going to trace out a circle. And as you can see, x of 0 is A and y of 0 is 0. So at t equals 0, it starts right here. And then it just goes around the circle. And you can ask me anytime t, and I can tell you where you are. Okay. All right.
Okay.
Now, 3D. Not much different. I have R of t is equal to f of ti plus y of tj. Nope, that's a g. Plus h of tk, where I get r is xi plus yj plus zk. And here x is f of t, y is g of t, and z is h of t. Okay. All righty. So here's the fun stuff. Okay. Let R of t be f of ti plus y of tj plus z. Oh my gosh, I don't know why when I get there, I just skip it. G plus h of tk. All right. Be a vector valued function okay, and let L, and L is going to be a vector L1I plus L2J plus L3K. Okay, be a vector. Then R has a limit L as T approaches T naught implies the limit as T approaches T naught of R of T is equal to L if for all epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of t minus t naught is less than delta, then the length or norm of r of t minus L is less than epsilon. Okay. All right. So if the limit as t approaches t naught of r of t is equal to L, that is the same as saying the limit as t approaches t naught of h of t, let's start with f of t is L1, the limit as t approaches t naught of g of t is L2, and the limit as t approaches t naught of h of t is L3. Okay, so this is not a hard concept. All right. It basically means the limit as t approaches t naught of r of t says find the limit as t approaches t naught of f of t, I, plus the limit as t approaches t naught of g of t, j, plus the limit as t approaches t naught of h of t. Okay. Okay. So I'm going to give you an example. In R2, r of t is equal to the cosine of ti plus the sine of tj. So the limit as t approaches pi over 4 of r of t is the limit as t approaches pi over 4 of the cosine of t I plus the limit as t approaches pi over 4 of the sine of t j. Well, this limit is the root of 2 over 2. And this limit is also the root of 2 over 2. So therefore, I get the limit as t approaches pi over 4 of r of t is the root of 2 over 2i plus the root of 2 over 2j. Okay, anything difficult about that? the limit as t approaches 0 of r of t is going to be the sine of t over ti plus 1 minus the cosine of t over tj. That's wrong. I want t, wait a minute. Nope, I want 1. J plus e to the t. Okay. Okay, so what is that limit? Well, you just got to compute them separately. So this limit as t goes to 0, well, that limit is 1. And this limit as t goes to 0 is actually 0. And this limit as t goes to 0 is 1. So this turns out to be I plus k. Questions? Any questions, Anaya? Naya?
Hello. Sorry.
Yes. Any questions?
No, right now I just saw the one from the pie report. I see how you got it. Use the trick circle, right?
What do you mean?
The pie report. You use the square
Oh
root.
yeah, I used it. Yeah, I did the sine. Yeah, I used the cosine of pi over 4. So
Okay.
yeah, this is cosine pi over 4. And then this one is the sine of pi over 4. And then I did direct substitution. Now on this second one, you have to use L'Hopital's rule to find the answer for 1 and 2. For F and G, you need to use L'Hopital's rule, but you can still find the limit. Okay, so that's how you find the limit. Okay. Definition. So after limits comes continuity. All right. A vector valued function.
Wait, I just got one more question. So the sine t over t, how did you get 1 for that one?
Aha, okay, so. All right, so I did the limit as t approaches 0 of the sine of t over t. And that gave me 0 over 0.
Oh yeah, and then you do the what's that, L'Hopital's rule or something like that?
Yep, L'Hopital's rule. So that's the limit as
So
t approaches 0. Derivative of sine is cosine of t. And the derivative of t is just 1. So that's now the cosine of 0 over 1.
Oh, okay. I just make sure. Thank you.
And that's 1. And I did the same thing with the magenta one.
Cosine.
Yep.
Okay.
I did the same thing with that one too. Okay. All right. Okay, a vector valued function R of t is continuous. Okay, at t equal to t naught. If every point is continuous. So if in its domain, all right, if 3 things happen. Okay, so the first thing is continuity test. R of T naught is defined. 2, the limit as T approaches T naught of R of T exists. And number 3, they're equal. The limit as T approaches T naught of R of T is actually equal to R of T naught. So all 3 things must happen. The function is continuous if it is continuous if it is continuous at all points T naught in its domain. So we can say it's continuous at a point, or we could say the whole thing is continuous. Okay? And then most importantly, the vector function, valued function, R of T equal to F of Ti plus G of Tj plus H of Tk is continuous if and only if F of T, G of T continuous at T naught. If and only if F of T, G of T, and H of T are continuous at T naught. So if one of them is not continuous there, be done. Okay, then you have to be done. All right, so example.
What sections are on the test?
Conic sections 1, 5 through 3. Uh-oh, let me see. Hold on a minute.
Did I say thank you already?
To who?
Oh, you, because you told me the section. Sorry, it's a
I didn't
lot going
finish.
on.
I didn't finish them.
Oh, you said 1.5 conic sections.
1.5 to 3.2.
This 3.2? Oh, this
This is
3.1.
3.1 we're doing right now.
You didn't open the homeworks. I couldn't do
I
that.
saw that. I gave you till Wednesday or Thursday to do it.
Okay.
Okay. F of Ti plus G of Tj. Oh, let me put some functions in here. this is kind of hard to come up with a good example. So I'm trying to find one. Oh, trusty, let me get my little trusty book. Get that I don't have to think of everything out the top of my head. I can use my book for some examples. I really don't have a whole lot of examples for continuity. Let me grab one off of here. Okay, here's a good one. Okay, so the first question is compute, number one, compute the limit as t approaches pi over 4 of r of t. Second question, is r of t continuous at t equal to pi over 4? And then third question, is r of t continuous at t equal to 0? Okay, so how do you do this problem?
So wouldn't you just plug in pi over 4 for the t and every
Okay, so
value?
all right, so in the first one, so in number one, you're right. You would just get r of pi over 4. Oh, sorry, I'm computing the limit. The limit t approaches pi over 4 of r of t. So for this one, we would just use direct substitution. So we would get e to the pi over 4 I plus the sine of pi over 4 j plus the log of pi over 4 k. Okay. And if I take the limit, oh, that was the limit. So is r of t continuous, number 2. Whoop. So is r of t continuous at t equal pi over 4? Well, r of pi over 4 is simply e to the pi over 4 I plus the sine of pi over 4j plus the log of pi over 4k. And they're equal. So the limit and the function value are equal. So yeah, that is the case. Number 3, is it continuous? So I need to find r of 0 is equal to e to the 0 I plus the sine of 0j plus the log of 0k. And I got a problem right here. So R of 0 does not even exist. So therefore, it can't be continuous. Not continuous at t equals 0. Remember, three things have to happen. The function has to exist. The limit has to exist, and they have to be equal. So in this problem, when I take the limit, I do direct substitution. That's the same as just evaluating the function. But in the third part, when I go to find out whether it's continuous, I see it's not even defined at t equal to 0. So no, it doesn't exist. Okay. So you have to be able to find the limit, and you have to be able to find continuity. Okay. Any questions about that? Hello. Okay. Okay. So we're going to go into calculus of vector valued functions. And actually it is just like that limit and continuity, except I'm going to do some derivations first. Okay. So let's suppose that R of t is equal to, and I'm going to do this in 2D, and then it translates to 3D. Okay. So let's do some 2D derivations. All right, suppose R of t is equal to f of ti plus g of tj. This thing translates to 3 dimensions, but this is a shorter and it doesn't take as long to do it. Okay, so this is my function, and this is a position vector. Of a particle moving along a curve. And f and g are differentiable functions. And I just realized I should have stopped. Hold on a minute.